Hey guys, today we're going to be talking about gas chromatography. So what is chromatography? Chromatography is used to separate the various substances of a mixture. One of the most common of these types of chromatography is gas chromatography. The purpose of gas chromatography, or GC, is to separate the compounds of a gas mixture, so that like each element of the mixture is able to be identified, and the purity of it is able to be tested, and how much of that specific element or substance there is. Um, the process of the machine, the chromatograph, hard to say that word, it separates the volatile gaseous compounds and that are carried by an inert gas. So the use of the instrument, the gas, the we're going with GC instrument separates the chemical compounds of a sample mixture, like I said in the previous slide. Then the compounds of this mixture, the contents, they're all identified. The quantities are identified for them. Um, Once they're all separated, a sample that contains organic compounds of interest is injected into the sample port where it will be vaporized. So if you look down at the graph down here, you see where it says sample and then the injector port. So that's what it's talking about right there. You inject it and then it becomes vaporized. The vaporized samples that are injected are then carried by the inert gas to the head of the chromatographic column. And so you can look down here, you see that little spiral thing. So it goes through that column to the head. And so then we have a new word here, elution. So elution is the process of extracting one material from another by washing with a solvent. So then there's some elution done. Um, it's present within the flow of these inert gases such as helium, argon, nitrogen, carbon dioxide, and hydrogen. Um, and that's used just to like get the purity of the compounds within it. So we know specific ones. It just like it helps to separate them.
Okay, so for the general process of you using the instrument yourself, first you have to turn it on and run a blank sample to make sure that there's no error. And then the sample, you mix it with a solvent, and then you place it into the instrument using a syringe. And then it will go through a tube with the inert gas, and it will end up in the column, which will produce a signal that is sent to the detector. And then the detector sends the signal to the recorder, which is normally a computer, and the computer will make a graph that we can interpret. So the graph will show a bunch of different peaks, which will tell you how much chemical is in each sample. And the higher the peak, then the higher the amount of that chemical in the sample. So they're proportional. And you can't see the specific amount of molecules shown by the peak, so you have to compare it to a baseline graph of a mixture that you already know the amounts. And then the first peak usually shows the inert gas, and then the rest of the peaks normally show the different compounds that are in the solution. And then variables that you can control include the temperature of the column, which is normally based on the boiling point of the mixture, and then the type and the amount of sample added, which is what you can control. And then you can also control the type of detector you use. Each machine has a different type of detector, so you'd pick the machine based off of the sample that you're using, and then the amount and type of gas that you use.
Okay, for instrument performance, we first start off with accuracy and precision. And before we get into that, I just wanted to state the simple definitions of accuracy and precision because many people get them confused. So accuracy refers to how close a measurement is to the true or accepted value, while precision refers to how close measurements of the same item are to each other. The accuracy and precision of results in GC are highly dependent upon the sample and its preparation, the instrumentation, accessories, and operator skill and experience. For these reasons, accuracy and precision can be expected to vary from one lab to another. Modern gas chromatography, I don't know what to do. Can you pause it? Modern GC are expected to deliver the highest performance levels, but actual performance can suffer due to a number of reasons. Overall, the GC is known for having high accuracy, and it is possible to achieve a precision of less than 1% RSD. For the example of accuracy and precision, I found a study where 5 labs evaluated the accuracy and precision of GC using urine samples with morphine, codeine, 6-acetylmorphine, and benzoylecgonine. You can see that the percent CV is used in the results, and this means the percentage of the mean represented by the standard deviation. The results show that within laboratory precision, represented by percent CV, was very tight with less than 3%. Between laboratory, percent CV was less than 10% for all compounds except 6-acetylmorphine. The average accuracy varied between 95.2 and 101.9. The percent CV accuracy was 3.44 for benzoylecgonine, 4.6 for morphine, 6.43 for codeine, and 5.46 for 6-acetylmorphine. Moving on to resolution. Resolution is the difference between peak retention times divided by the average peak width. Changes in resolution are due to changes in peak separation and/or peak width. If the increase in peak separation is greater than the increase in peak width, improved peak resolution occurs. Lowering column temperature is a common method to improve peak resolution. Using the GC, resolution can be improved by changing the temperature, decreasing the height of the column, or increasing the number of theoretical plates. If you look at the picture to the right, I included, there is a 2.3% mutual overlap and the resolution is 1. And then the one next to it has 0.15% mutual overlap and the resolution is 1.5. So you could say that the higher the resolution equals less mutual overlap. Moving on to sensitivity. Sensitivity is specified as a signal to noise ratio, or SN. Lowering the background signal originating from the GC and improving the GC resolution can improve its sensitivity. Achieving the highest possible purity in the carrier gas helps to decrease noise, specifically chemical noise. For example, carbon dioxide gives a background signal at MZ44, or mass divided by charge number. That increases the chemical noise. Oxygen degrades the column phase, which results in increased bleeding. That is the background signal at MZ207. The use of high purity gases with appropriate filters can significantly lower the GC background signal and therefore increase sensitivity.
Okay, and now I'll be talking about real-world applications from our primary literature, and these include usage in clinical and pharmaceutical environments and environmental and forensic environments as well. Okay, so in clinical and pharmaceutical settings, GC can be used for quality control, to check for the purity of different drugs, and just to make sure that the chemicals are all able to be made in large batches safely and that they don't have any toxins in them. And they're also used to make sure that the quality of the drugs is going to stay consistent. GC has also been used for environmental purposes more recently, because it allows for environmental scientists to monitor levels of pollutants in the air and in the ocean, and it kind of allows them to visualize where the pollution is worse. And using this data, they can keep track of how it changes throughout the years. GC is also used a lot in forensics. For example, this is used very commonly to take samples of blood and different fibers from crime scenes, and they can analyze them using GC. And this has a lot of different important uses, like determining someone's cause of death, seeing if maybe they ingested poison or consumed drugs or alcohol, and it just allows them mainly to determine cause of death and see what kind of samples were in their bodies. I also included this example because I think a lot of us didn't realize how much GC really affected our day-to-day lives. But GC is actually used commonly in the food industry to ensure the safety of food, so it's very important. It just allows us scientists to see how the quality of food is and detect any contaminants, make sure that the flavor and aroma is consistent, and it also allows them to control what kind of natural bacteria, good bacteria versus bad bacteria are in the food. And here I just included some pictures, kind of a segue. As they talked about earlier, all the gas comes from the cylinder, then it goes through the GC, and then all the data is sent to a data processing unit, usually just a laptop. So here is an example of the data that they used in our primary literature. So for this table, it's kind of just showing how absorbents can be classified according to their structure. Because in GC, the retention of compounds is determined by the chemical nature and then the physical pore structure of the gases, and the molecular weight of the molecules are very important, and so they have to keep track of all this data whenever they're using GCs. And then this is another kind of data. So they also have to keep track of the specific surface areas whenever they're using GCs. And the specific surface area is just like the quantity of the surface available for the application of the gas or whatever, the blood sample, whatever it is that they're measuring. And it has to be known if they want to interpret the physical and chemical interactions that are happening in the materials. So yeah, they have to use these two types of data in order to make the conclusions with the GC. And here's a graph of what that looks like. This is all they can run this through the computer, and this is kind of the actual picture that scientists get from the machine. And here are our resources, our primary literature and the rest of our resources, the pictures. And that's it.